I'll give you some information about the Euclid Mission with some focus on some peculiar activities that sometimes are shown in usual meetings, in general meetings about Euclid, because I can find a lot of information on Euclid in papers of most of you is involved in Euclid or as got information about it. Euclid was conceived in 2007 as an Italian proposal for the copy part and a French proposal with participation of the imaging part, and then after selection, I mean, starts implementation. So a lot of people have been present in the Euclid. So I would say give some highlights on the science goal with specific emphasis on the Italian contribution to the Euclid, Italian involved, and associate to INAF on it, in INFN to it, and then some say some bits of the technology which is embedded in the Euclid Mission. I'm on the experimental side, contributing to one of the two instruments on board, and so that's something that is very, very close to my experience, and I would like to highlight how complex and how sophisticated Euclid is. And I will touch two of many topics that you can say be interested in Euclid. I mean, or something which is really tricky is the Euclid survey strategy, an activity which is led by Roberto Scaramella in Rome, and some say an example of the systematic effect evaluation. I mean, the calibration effect is a work done by a graduate student that worked with me in the last year, and then some pictures, some things of who is building Euclid, because Euclid is being built in these days. Okay, just a couple of key questions on which Euclid is conceived. So the idea is lambda, the cosmological constant, into small and fine-tune it. So what's about lambda? It's something which it comes from a dark energy. We actually don't know. So we say model that with dark energy as an equation of state with W, with a constant part and a variable part, and we characterize our knowledge of the equation of state by the figure of merit, which is inversely proportional to the uncertainty that we have on the determination of the two components of that. So is this equation of state something which is static or something evolving with time? This is one of the key questions that we still have today, because the say data we have now has an error on the constant part of about 10% and even larger on the variable part. So the goal of Euclid, that we'll see in a moment, for the figure of merit is to reduce this uncertainty and get a figure of merit on Euclid data alone of around 400 to 500 alone. This is a large improvement with the present situation. So how we will do that? What is the machinery that produced this improvement in our knowledge of the dark energy in specific? Euclid is based on two complementary observations. The space-based one, which is mainly the vis imaging and the near-infrared imaging and spectroscopy, which is not possible for the ground, for the visible part, for the stability of the optics, and for the imaging part, for the infrared part, because of the transmission of the atmosphere, which is not allowing such observation from the ground, and complementary ground-based observation that will give us both, say, calibration spectroscopy and imaging and photometry, which is complementary to the near-infrared one. So this will be translated in probes that, for the imaging parts, will be mainly on the cosmic shear for the redshift survey, the determination of the power spectrum, and other probes that are getting more and more important from the cosmological part, like the clusters and the interstellar, say, supernova and integrated Sachs-Wolf effects and other effects. So the ultimate goal we have is to test the fundamental physics theory using the Euclid data complemented with other observations such as Planck, Rosita. And I will touch briefly in a moment the immense legacy science that can be done on Euclid data. So what we will obtain at the end of Euclid survey, in the nominal one, is a wide field survey of the extragalactic sky, mainly of extragalactic sky, in which we will get images of billions of galaxies to extract the deformation due to weak lensing, and millions of spectra. So the limited magnitude in the visible and the near-infrared are reported here, that also on spectroscopy. One of the key points we have at this Euclid is designed to have a wide survey and deep fields, mainly for calibration, but of course it can be used also for science, and slitless spectroscopy. This is of course a compromise between the quality of the data that we can get and the complexity of the mission itself. So at the end, what are the probes that we want to get, the cosmology probes that we are exercising that? So one of the main probes is the Bionic acoustic oscillation as a standard ruler. As we know that we know the standard ruler on the cosmic microwave background, and the Planck satellite did that with extremely high accuracy. And I'm proud to say that I've been part of that mission in the beginning of my scientific career. But of course, this is imprinted in the say position of the galaxy, in the distribution of the galaxy in the sky. And so by this that we can call a 3D map of a universe, this kind of tomography, we can reconstruct as a function of redshift the position of the peaks of the baryonic acoustic oscillations. And so at the end, we can probe with Euclid part of the redshift range, which is beyond what has been actually explored with ground-based measurements. So what is outside that with great accuracy because of taking advantage of this large survey. So it's not only the expansion of a universe that is depicted here, but of course how the structures are clustering and are built along the evolution of the universe give us some hints, the gravitation theory which is behind that. And this is something which is of extremely high importance, that touches the fundamental physics. I'm not talking here of other science goals such as the characterization of neutrino species and mass of neutrinos, sum of mass densities are a lot, but it is much more on that. And one of the other points is what is called redshift space distortion. Italy and Italian researchers have a long tradition on this kind of observation done with the survey, say galaxy surveys, spectroscopic galaxy surveys. But what Euclid will do is to extend and reduce the uncertainties of these measurements up to redshift of approximately 2. So it's something that is, say, we are awaiting this data, which are not available yet. These say, pictures are coming from the original proposal that was submitted to ESA and refined later on for the adoption. And of course, more and more data and simulations and forecasts are being produced in these days. You can find on the IDS a lot of papers on that. The other probe that we have is the on the Euclid side, the weak lensing probe. I'm touching that because there are a lot of people which is involved with also in Italy, even if the core of the science is done in collaboration with other groups in France and the UK. But of course, there is a lot of people working on that. And these are two complementary probes. The potential of Euclid is to have in the same mission two orthogonal probes, let me say, and two instruments with completely different systematic effects. And so we can cross-check the data, like, of course, we did in Planck with the two instruments. So in the same mission, it's a way of having two complementary data sets that can be cross-checked and improve the accuracy. This potential is extremely high. No other mission at present had such a complementarity. That's extremely important. I will not enter the details of how the distortions are made, but just to let you know that when this depict this picture, how these things are done. Of course, there's a lot of systematic effects, again, also in these measurements that are treated in the complex pipeline, data reduction pipeline that the Euclid mission has. Again, I have no time today to enter the details of how the pipeline is built, but just to let you know that the data from the spacecraft are injected in a system that first extract the information both on the visible side, the images, and on the spectroscopic side, extracts the spectra, and then combines with the infrared photometry, ground-based measurements, and then extract the products at the end. So just to have a summary slides to summarize what are the improvements that we expect to get from Euclid, is that, as I said, with the different probes, I just highlight the dark energy figure of merit as a number. Euclid alone will get up to 500, while if we combine with other data sets, for instance, Planck, which our Italian community in specific has a large experience on, we get to an improvement and to a figure of merit that can reach 6,000, which is an incredible improvement with respect to what we have now. Of course, we have improvement also on gamma and other parameters. So this will allow us to test the gravity theories. Are we living in a constant lambda or not? These key questions, we will be able to answer with the Euclid data. Just to touch briefly the Euclid legacy, because of course this wealth of information that Euclid will produce, of course it will be available to the scientific community to do other science, and of course this is we can consider it a mine that will be useful for many years, I hope, to extract the information, because as you see, the limit magnitude is not so deep as other surveys, but the surveyed area is very large, both in imaging and photometry from sky, with an extremely high accuracy and control of systematic effects. And this will be also done in combination with other surveys on ground that had reached agreements with the Euclid Consortium for the common exploitation of the data that will be used for Euclid science, but at the same time, these data will be Euclidized, as we say in our jargon. That means that this will be made compatible with the Euclid, so to the same level of systematic effect control. So you will find an homogeneous set of data that I think it would be extremely important for many scientific topics. And I think that even people not involved in cosmology or in galaxy evolution will find interesting this data set in the future. So now let me just, I hear an echo. Maybe somebody has a microphone which is open. I don't know if you can check, if you can close your microphone. Okay, now it's much better. It seems to be better. Okay, some information, say very high level information of the Euclid satellite. This is say a CAD model of the Euclid satellite made by Thales. Euclid Mission was selected in 2011 and fully funded. And of course, we had two European industries that are building it, Thales Alenia Space in Italy and the Airbus Defence and Space in France. And a contribution of the instruments and the ground span segment is provided by the Euclid Consortium. So it's a medium-sized mission, a mass of 2,000 kilograms overall, a couple of thousand watt at the end of life in solar power used on board. The data rate is quite large because we will acquire images, as I will in spectra, and I will tell you in a moment how we will do that. So it's quite large. We'll have a 4-hour visibility every day, and this amount that will also increase on ground with the combination of ground-based data. The telescope is passively cooled to 125 Kelvin by radiator, which are these say plates here in green, light green here. Probably you can see my mouse. And the telescope is it's rather small with respect to the possibility, but of course this compromise with the mass and the complexity of the satellite is 1.2 meter primary mirror. Is a Cortian astigmat off-axis mirror. It's a wide field, high stability mirror made out of silicon carbide to get the stability that we need for the weak lensing measurements. The thermal stability and optical stability of the system is one of the key design factors for the Euclid payload at all. The mission will be launched with a Soyuz frigate launcher, and the transfer orbit will bring it to the L2 position. Will essentially orbit around the Lagrangian point 2 of the Earth-Sun system, and so it will be far from contamination from it's an orbit very stable for the temperature from contamination from the sun, the moon, and the solar system, and especially the Earth and the moon contamination, which would impact on the temperature stability. So it will point always in the solar panel will be exposed to the sun, and the telescope will be always shaded, and will observe orthogonal, almost always orthogonal to the plane of the orbit. So the two instruments on board is a wide field instrument, this instrument, visible instrument made out of 36 4K by 4K CCD with a wide filter, and it's probably the largest camera ever flown on a space, a scientific space mission. And there will be also the infrared instrument, which is a combined photometer and spectrograph. The photometric part is a 3-filter Y, J, and H filter, which illuminates 16 H2 RG teledyne detectors, which are the most sensitive infrared detector in this wavelength range. But with the interposition of grisms we have 3 red crisps and 1 blue crisp, we can get a slitless spectroscopy. As you probably have heard, one of the Euclid crisp had an issue, a design issue actually, so it's not usable, but a strategy to use the combination of the other useful 2 crisps, red crisps, in a different orientation. I will show in a moment how this is obtained. Gave us the possibility of recovering the full mission capabilities. There is also a blue crisp, so in the blue part of the spectrum, that will be used in the deep fields, mainly in the deep fields, and will be extremely useful for, say, galaxy evolution and the astrophysical part, more than for the cosmological part. But this is a complementary to the other part. The white survey will be done with red crisps. So the main survey will cover 15,000 square degrees, and we will have 50 square degrees on 3 deep fields, 1 north and 2 south. And we will see in a moment when we will touch the survey strategy where these are located. Let me show you some pictures of Euclid Satellite. This is the structural thermal model, which is the, say, sort of simulator. This is form and fit, as we say, as the real satellite. You see the large sun shield that actually is being refurbished and will be used on the flight model. So it will fly with the Euclid Satellite. We have the say the baffle around the telescope and the payload module, which is made on silicon carbide. And you see also this golden, say, object here below the optical bench, which is the NISP instrument, the near infrared instrument. And below that is the platform, as we say, which contains in the panels all of the electronics units. This is another view of this instrument tested at Alenia Alenia Space in Cannes. This is the, say, a CAD reconstruction of the Euclid payload module, seen from the bottom. You see that this instrument here is the large camera, and you see the folding mirror, FOM are the folding mirror, so the light is coming from the bottom of the pictures, is folded in these 3 mirrors. There is a dichroic which separates the 2 bands, just in front of an NISP instrument, which is here on your right. And we will see in a moment how the NISP instrument is built. By the folding mirror, the light from the sky is directed into the VIS instrument, which is here, and with this shutter in front and a calibration unit here at the bottom, this sort of ball here close to the folding mirror 3. The radiators to cool down the VIS and the NISP detectors close to 100 K are say, depicted here at the bottom. There is cold electronics on both instruments, say close to the detectors. Here you see the flight model of the near-infrared spectrophotometer NISP, where Italy had a large contribution. We provided the CRISM wheel, the wheel that is displacing the dispersers in the optical path. The optical path. We have here the 2 lens assembly, the collimator and the camera ones, and you see this complex silicon carbide structure which holds the detector at the bottom. This is the flight model almost 1.5 years ago. Then it was submitted to the full instrument level test. and here Italy, with the contribution of INAF and researcher, gave say a major contribution to that. Our provision, Italian provision to the Euclid Mission on the instrumental side is providing the data processing unit hardware for the NISP instrument, and both application software on board on the ICU application software, say developed at the Observatory of Torino, and the application software on the data processing unit, which was built at the Observatory of Padua under the supervision of the late Fabio Bortoletto and Carlotta Bonoli, and the responsibility has now moved to the OAS Bologna, now where the group is being based, with still some contribution for the Observatory of Padua, of course. The other contribution of the VC instrument is the electronics, the warm electronics built at IAPS. We say the Italian country, the hardware was built by the industry, but the application software by the team by Anna Di Giorgio at IAPS. So a major contribution on both instruments. The responsibility in Italy also lies in the leadership of the science ground segment, which is of the Observatory of Trieste, and the ground segment manager, which is Andrea Zacchei. So this is the final picture of the NISP instrument with the multi-layer insulation on board. Just a small peel of what is the quality of the NISP instrument. You can see here the encircle energy of the optical image of the PSF measured during the cold test. And as you can see, really we are much better than the acceptance values to the requirement, and we are very close to the theoretical ideal system. And that's an incredible result, because this has been designed but measured at operating temperature. So this will say that Euclid will say is exceeding the requirement, especially in the near-infrared part. You probably have heard of some issues on the visible instrument. This will be fixed as there be cold tests that are being done on the payload model by exchanging the, say, failed cold electronics. Other pictures, will go quite fast on that. This is the real telescope while being assembled on the optical bench on the left, on the right. And here you have a different mirror, folding mirror, the visible shutter, calibration unit, and the NISP assembled on the optical bench, and the visible camera on the top right. You see, as any complex instrument, how complex is the system and how accurate is the say integration that is needed for that. This is a very recent picture. This is the collimator of the telescope, and the telescope and the Euclid payload is enclosed in this large baffle on your left, with the electronics, the flight electronics, mounted on a panel on the back part. In these days, the Euclid payload is at CSL in Liège and is being tested for cold operations with the telescope, which is, of course, the final cold test of the system, final performance test. See other pictures of the collimators. And here you can see on top the two units built by Italy, the data processing unit and the instrument contributed with the software on board, and below you see also the data processing unit for the VC instruments and the harness we have. Just to tell you that this is the say a reference schedule that we are completing the integration. The launch is still planned within 2022 with an operation of 6.15 years. And you'll see we will release data after the second year. So data will be public quite soon after the first reduction and, of course, exploitation by the team. So let me touch this in the last part of the talk, 2 points: the Euclid survey strategy and its wavelength calibrations. Just to tell you that what is the issues we have. These are the 2 focal planes, the 36 CCD and the 16 detectors. You see there are gaps between the detectors, and of course we have to cover these gaps. So the strategy is done by tethering the satellite by a little amount around, I mean, the nominal, say, pointing position. So we'll take 4 images for each field, and of course we'll take 4 different spectra for each position with different orientation of the GRISP. So the dispersion direction will be different. That's because the slitless spectroscopy otherwise will introduce confusion, because spectra are overlapped. But if you change the dispersion direction, of course you can disentangle much more spectra from that. This is one of the reasons why we have this orientation of the spectrum. So we will obtain for each field of view 4 that we call dither. You see the large field of view is larger than the full moon, and we'll obtain a visible image, 3 photometric image for each dither, and a single exposure in spectroscopy. So for each field of view, 4 exposure in spectroscopy, 3 by 4 exposure in photometry, and 4 exposure in imaging for 20 observation per day. It's each dither, its single exposure is around 600 seconds. And you see here how complex it is to cover the 15,000 square degrees in the extragalactic sky, because of course this is a cosmology mission, so we need to observe regions not contaminated by the galaxy and not contaminated by the zodiacal light, which is one of the major contaminants from the astrophysical point of view. So how we get there? I saw that I already said that the satellite will be observing orthogonal to the direction of the vector containing the satellite, the sun, and the Earth. So it will orbiting around like Planck. We will be following the Lagrangian second point, and so we will be observing strips, say orthogonal to that. So how this is built? Just to let you know, these also the deep fields, the green one, the Fornax one, and the deep south field, and the north field. Deep field is here, has been selected to be best quality in terms of the possibility of calibrating the cosmological part. So we have to make this observation, but at the same time we have to fit periodic calibration observations to ensure that the stability of the calibration and the accuracy of the calibration is maintained throughout the mission. So let's imagine how complex in this year is to fit all this calibration with the constraint of the orbits, constraint of the orientation, constraint of the field to observe. This work has been done by the Survey Strategy Group, led by Roberto Scaramella, with a Portuguese contribution by Ismael Terreno in Lisboa, and they actually succeed in placing the fields to avoid any gaps in the coverage of the sky that will introduce systematic effects in the statistical statistical evaluation of the results. I mean, which is of course dependent also on the coverage of the sky and on the completeness of this coverage. And as you can see, the algorithms first defines where to observe, then defines how to place the orientation of a field of view, and then the trails that are to be followed in the different part of the sky. It's an extremely complex system, and what we get At the end, this is the results of a simulation, the possibility of covering the sky the first year, second year, including the deep field, the third year, the fourth year, the fifth year, and eventually the sixth year, reaching the full coverage. So the constraint on having just 6 years is very stringent. Of course, the mission has on board resources to go also over the planet lifetime, but of course this is dependent by many considerations, of course. And this is just to let you know how complex it is to do that and to cover this part in 6 years. Okay, much more information can be found in papers written to describe that, and there is a paper on the survey strategy by Roberto Scaramella and collaborators. Let me touch it just for the last few minutes. I'm close to the, say, 40 minutes, so I will just briefly touch this as an example of systematic effects consideration is the stability of the calibration. So we have a goal of monitoring the stability of the calibration in every image. So the work that is done by Benedetta Valerio at the University of Genova is how to evaluate from field stars the stability of this spectroscopic calibration. So the idea is that we simulate the spectra, we then introduce systematic effects on it, effects that are distortions of the spectra, spectroscopic and astrometric distortion that moves the spectra from the, say, nominal position. And we also can simulate some instrumental effect on it, dark current, nonlinearity, readout noise, the background noise. These have been, it's a machinery to introduce this effect. We simulate the observation of the NISP instrument. Sorry, I was not mentioning that is done for the near-infrared instrument, the spectrograph, of course. And then what we obtain by correlating, cross-correlating the peak position of a shift is the magnitude of the effect as a function of the magnitude of a field star. Of course, you see in gray the, say, nominal simulation without effects that, of course, has some intrinsic effects that are, say, non-ideality due to the fact that there are gaps between detectors, so the spectra are broken, so not every spectra is correctly reconstructed. But of course, we can determine the effects of the presence of systematic effects and distortion. If we look at the uncertainty of the error of the width of this correlation function as a function of the magnitude, we can go on determining which is the magnitude limit in which we can accept and consider the calibration, the wavelet calibration monitoring by using field star as stable. And I will show you these results that show you that the effects which we found most impacting that is the presence of systematic effects, noise and instrumental effects, more than the distortion. So the effect of the distortion is already well considered by the reduction pipeline. You see here in these other plots the effects of the presence of the gaps in the detector, and at the end the results that we got by clipping, applying an iterative process in clipping the spectra that we don't want to use, but because they are contaminated, you can easily see that the effect is dominated by the instrumental effects more than by the distortion, to a magnitude which is around 16.4. And this calibration monitoring will be eventually implemented in the Euclid pipeline. Just to finish with the presentation of the Euclid Consortium, which is a very large consortium. Now we reach 2,000 members. I think this is an old figure. The number of people working on Euclid is increasing more and more when we are approaching the launch. And just to touch what the survey we did recently while preparing the schede, as people in INAF knows, we have around 170 people working on Euclid, registered people working on Euclid. Number of FTE that you can see every year is this one. From my point of view, is quite impressive. Also considering the way these are evaluated in the system, there is probably underestimated. And I would like to mention the other responsibility that the Italian say community has, is the responsibility on the instrument operations team, especially for in general, and for the NISP instrument, which is based in Bologna, and I'm leading this effort for the flight. And we have, of course, the Science Data Center, which will be based in Alter, and of course, this is a contribution funded by ASI. And of course, we have these organization units, which are the building blocks where the software and the data reduction pipeline is produced, the operational units, which are the infrared spectrograph, the near infrared units, the merging unit, and of course the level 3, which is the place where the say most of the science is extracted from the data. Science working group, which are preparing the exploitation. Of course, we are leading galaxy clustering with the long tradition we have in Italy, clusters here in Bologna. The University of Bologna is leading there. And of course, a large contribution on the cross correlation with the CMBA fundamental physics, legacy science, galaxy evolution, the strong lensing, which is led by Massimo Meneghetti here in Bologna. And of course, we have in the IST, which is a jargon of Euclid Mission with likelihood for the galaxy clustering, and of course the survey team leadership. Just to pop up a picture that we all wait to get it again, which was the last meeting in presence. And these are the acknowledgements. I thank you for your attention. And